Hey, Cole.
Hello.
How you doing today?
I'm doing pretty good.
How's school going?
It's going good.
All right. Let's just review. If P then Q, what is the inverse of that?
If not P, then not Q.
Here's the clue. The word con means not. So those two are the ones that have not in them.
Okay.
Which means inverse does not have not. So what's the only thing it could be?
If Q, then P.
Converse would be what?
If not P, then not Q.
Correct. And contrapositive.
If not Q, then P.
If not Q, then not P.
Not P.
In other words, both of these have two nots in them.
All right.
Okay? And that's really the easiest way to remember it. If you remember that you need the word con and it's got a not in front of both, and if inverse is just switching the two, then converse has to be this and contrapositive has to be this. Which one of these three is always true?
Contrapositive?
Yes. That is usually not true, and that is usually not true. In fact, one of the great gimmicks of advertising is to state the inverse and converse, and people assume that they're true. Because most people, if you said if P then Q, they would say, well, okay, then if Q then P is probably true also. But most of the time it's not. And that's one of the great fallacies of logic, is that this is not true. Occasionally it can be. If the statement is if P, then if and only if P, then Q, usually means that the inverse and the converse are both true. Okay? All right. Let's go on. Where are you in the book right now? What subchapter? Are you at 2.6, 2.4?
2.3 or 2.4.
Okay. I'm going to skip ahead to 2.
We just finished like 2-column proofs and stuff like that.
Good. There's an easy way and a hard way to learn 2-column proofs. The easy way is where they give you a 2-column proof and one of the columns is filled in and you just have to fill in the other column. In other words, if you do a number of these, you kind of get the hang of it. But if you have to fill in both columns, like this problem here, these are the ones that drive people nuts. So, let's do the 2-column proof where one side is filled in. And I'm not sure, you may not have, you know about parallel lines?
A little bit. We haven't really gone over it in the definite in terms of proofs.
Okay, let's go over it, you and I. We went over it this summer. But it's a critical thing. If you have two parallel lines and a transversal, okay, very important. This has nothing to do with proofs, by the way. When you cut two parallel lines with a transversal, you create 8 angles. But you really only create 2 unique angles. You create 1 and 2. And everything else is equal or congruent to either 1 or 2? Well, it's easy enough to figure out how. 1 is the obtuse angle, 2 is the acute angle. So if I want to know which one 8 is equal to, which one is 8 equal to?
1.
Okay. In other words, 1 is equal to 4, because they're vertical angles also. And 4 is equal to 8, because they teach you those are corresponding exterior angles. When they teach you this, they're going to give you a name for each of these angles. And I don't really like that. I really prefer the method of you really only create 2 angles. Every angle here is either 1 or 2. And more importantly, 1 plus 2 equals 180. So I could say 1 plus 6 equals 180 also. So this is an extremely important premise that when you take your ACT test, there'll be at least 6 questions that require you to know that.
Mm-hmm.
So this is definitely one of the things they test you on repeatedly. So starting with that, let's go back and look at this proof here. The only reason I'm jumping ahead is because by next Monday you may be beyond this already. And I really do feel like this is the best.
She said by Friday we're going to be done with proofs.
Okay, good. That's the perfect time. Then today is the perfect time for us to go over this. And that is the beauty of proofs. You won't have to, once you're done with it at the end of Friday, you'll be pretty much done with it forever. There is no point in future mathematics where you have to do these 2-column proofs. I mean, maybe if you got a PhD in math, you might have to. But certainly not, even if you were to become an engineer, you would not have to do 2-column proofs. And you don't have to know how to do these for the ACT. You have to know how to do these for one thing and one thing only, and that is this week's geometry test. And maybe the chapter test or the semester test. They may give you one proof on there. So let's go through how you do it here. First of all, if you remember a few weeks back, I showed you this. Have you re-seen this? This is in chapter
Those are the different properties.
2.4. Yeah. No, let's just review this a little bit. First of all, the first 4 don't require you to memorize. That just means that if you have an equation, you can do the same thing to both sides of the equation. You can add numbers, you can subtract numbers, you can multiply both sides, or you can divide both sides. That's all those 4 do. The difficult ones are these next 4, because you have to know them once, and that's about the last time you ever have to know them. In fact, I have to be looking at them to remember what they are. Okay? But unfortunately, you're going to have to memorize them. So the reflexive property, just remember that that's the one that says a number is equal to itself. Might sound silly, but that's a property. Symmetric property means that you can reverse. If A equals B, then B equals A.
We've gone over this a fair bit during class as well.
Okay, so you are familiar with those. Okay, so let's set those aside for a moment and see if we can do this 2-column proof. What's the reason for number 1? Number 1 says A is parallel to B, and angle 2 is congruent to angle 3. So that's given.
Yeah, it's a given statement.
Okay. And if you go to the last step, this is what we're trying to prove. Okay. So why is number 2 correct? Why is the measurement of angle 2 equal to the measurement of angle 3?
Because parallel lines with the...
No, this is a little bit of a, not a silly one, but one that's difficult to distinguish. First of all, understand the difference between congruent and equal. Okay? Remember what was given was that angle 2 is congruent to angle 3.
Oh.
So you have to show that that means the measurement of angle 2 equals the measurement of angle 3.
Oh.
And that's because of the congruent angles are equal theorem.
Okay, we haven't gone over that theorem, so.
Well, that's okay. The fact that you may not have all these theorems isn't really important as much as you see how the two-column proof unfolds.
Yeah.
And how much detail you have to do. In other words, you can't just assume that the measurement of angle 2 is equal to the measurement of angle 3. You have to actually state that and back it up with a theorem. And that theorem is going to say something to the order of congruent angles have the same measurements. All right, number 3. Angle 2 and angle 4 are supplementary. That you might not have had that either, and that's why I went over this. Notice that angle 2 and angle 4 are, you'll learn that those are corresponding interior angles. And because that angle is supplementary to that angle, and that angle is equal to angle 2, and angle 4 is equal to that angle, then angle 2 and angle 4 must also be supplementary. So the reason for number 3 would be the definition of parallel lines. And let's see if that's in. Have you had that yet?
Yeah, what we just kind of talked about is if it follows the definition of what is being stated.
In my book, see, I didn't get this problem from my book, your book.
Okay.
I got it from a good proof that I had in the past, one that had at least one column filled in. So this actually might come beyond chapter 2.4. In other words, probably the next thing you're going to learn is this part here, the parallel line stuff.
Mm-hmm.
Okay? Well, I could say that angle 3 and angle 5 are supplementary because consecutive angles of a transversal of two parallel lines are supplementary, or something. You'll learn what it is. You'll learn the exact theorem, and I don't really care what the exact theorem is. You know, the only thing that's really important is that you know that 3 and 5 are supplementary, 3 and 6 are the same, 4 and 7 are supplementary, 3 and 7 are the same. In other words, that's what you need to know, is which of these 8 angles are equal to one another, and which can you figure out, therefore must be supplementary. The most important thing is to know that 1 and 2 are supplementary. And I don't even know what the exact theorem is. It's not important. But that's what would go there for a reason, is whichever theorem states that 2 and 4 are supplementary. There. Not number 4, though. Number 4 is not the correct reason for number 3. However, what should the statement be for number 4? Definition of supplementary angles. What goes right?
Angle 2 and angle 4 equal 180.
You got it. Perfect. Angle 2 plus angle 4 equals 180. Okay. Now, what goes in number 5? If we're using the substitution property, and let me bring it up, this is the substitution property. If that's going to be the reason for the statement, If A equals B, then A can be substituted for B in any equation or expression. So that's the reason for that. So what goes here, you suppose? And look at the next one. The next one says 3 and 4 are supplementary.
Oh, you could you replace the 2 with the 3?
You got it. So number 5 would be angle 3 and angle 4 are supplementary based on the substitution property. Okay. Now, number 6 says angle 3 and angle 4 are supplementary. What goes here for the reason?
Isn't that just the definition of supplementary?
You got it. Definition of supplementary angles. In other words, the statement 5 said that angle 3 and angle 4 add to 180. Therefore, angle 3 and angle 4 are supplementary because the definition of supplementary angles. Finally, the last statement is the one we're trying to prove, which is that C, line C, is parallel to line D. And the reason is, well, the reason is this. If I say I have 2 lines, and I don't know if they're parallel or not, but if I put a transversal, and this angle 6 is equal to this angle 11, there is a theorem that says that means that line is parallel to that line. In other words, you cannot have angle 6 equal to angle 11 unless these 2 lines are parallel. And that's pretty common in geometry. When you have a geometry theorem, usually there's something called a corollary. It's like, you haven't probably had the Pythagorean Theorem yet, although you may have had it previously in math. Pythagorean Theorem says that
A squared plus B squared equals C squared.
If that's a right triangle. Only if it's a right triangle. Which means if I give you a triangle and A squared plus B squared is equal to C squared, that means this has to be a right angle. In other words, it goes both ways. If it's a right angle, then A squared plus B squared equals C squared, or if A squared plus B squared equals C squared, then it's a right triangle. Both ways. In other words, you cannot have a 3, 4, 5 triangle without it being a right triangle. If you're looking at some figure and you see some oddball triangle that nobody's defined, and one side's 3, the other one's 4, and this one's 5, you know you got a right angle in there. Has to be. You cannot draw a 3, 4, 5 triangle without it being a right triangle. Same thing for parallel lines. If you have those angles equal to one another, then you have parallel lines. If I go all the way back to my beginning, this example right here, and I say, let's take away the parallel marks, and I say that 1 is equal to 8, then those 2 lines are parallel. If I say 2 is equal to 3, does that mean the 2 lines are parallel?
No.
No, exactly. And the way you figure that out is,
really
can I alter the orientation of that? Yes, I could. And 2 is still equal to 3. So 2 being equal to 3 does not mean those lines are parallel. 2 is equal to 3 because vertical angles are equal. There's a theorem that says vertical angles are equal. But if you're comparing one of those angles up there to one of these angles down there, and you find the equivalent, then you can state that those are parallel. That's basically the last step here, is that they're trying to prove that C is parallel to D, and the reason is the corollary about parallel lines and angles, which you haven't learned yet. But this is a great problem for teaching people two-column proofs, because you kind of get a little bit of a hint with each one. In other words, if I have to go back to here and do a two-column proof, much, much harder. Let's try it. We're trying to prove that AB is parallel to CD. And we're given that 1 is congruent to 2, and we're given that 3 is congruent to 4. So what would be the first statement? Hold on a moment. Let's just... So what's the first statement? What do you think?
Let
me give you
angle 1 is congruent to angle 2, and angle 3 is congruent to angle 4 is given.
You got it. That's always the first statement, is whatever is given. What's the next statement bound to be based on the last problem we did? Remember the last problem?
Oh yeah.
We went from 1 to 2.
So the measurements of angle 1 are equal to angle 2, and the measurements are equal to angle 3 to angle 4.
That's the one that is a little tricky, because most people just assume that. They don't feel like they have to make it a separate statement. And the reason is congruence means equal. Basically. I mean, I'm sure the official reason is more elaborate than that. What did they say on the last one? No, they didn't. That was the one we had to come up with the reason. Okay. All right. So, statement 3. Remember, ultimately, we're trying to prove that line AB, line segment AB, is parallel to line segment DC. Well, what would we need to prove that? If you look at these 4 angles, what's this fourth statement going to be? That's the easiest way to do this one. If angle 1 was equal to angle 4, if the measurement of angle 1 was equal to the measurement of angle 4, then that would mean this is parallel to that. Because notice that this line AC is the transversal.
Oh, okay.
And if that's a transversal, then 1 is equal to 4. Or if 1 is equal to 4, that's a transversal between 2 parallel lines. So I can say statement 4 right now. The measurement of angle 1 equals the measurement of angle 4. That would mean that AB is, excuse me, hold on, I'm a little bit backwards here. The final statement always has to be what you're trying to prove. So this has to be the final statement. Okay? And the second to last statement is going to be the measurement of angle 1 equals the measurement of angle 4.
Mm-hmm.
Why is that?
It's because I can't remember what the line is called, but with that one.
In other words, for the same reason on the previous problem, the substitution property was the reason that 3 was supplementary with 4. Because we proved that 2 is supplementary to 4, and 2 is equal to 3, and so 3 must be supplementary to 4 because of the substitution property. Well, here I'm saying that the measurement of 1 is equal to the measurement of 2, and the measurement of 3 is equal to the measurement of 4. Therefore, the measurement of 1 is equal to the measurement of 4. Hold on a moment. If we knew that 1 was equal to 4, then we would know that AB is parallel to CD. So we have to prove that the measurement of 1 is equal to the measurement of 4. Hold on. Yeah, 2 is equal to 3. That's the middle one. We didn't prove that.
Okay, yeah, that's what I was kind of thinking it was.
Measurement of angle 2 is equal to the measurement of angle 3 based on what reason?
No,
vertical angles.
Vertical angles, okay. Oh, yeah, okay.
And actually, there seems like there has to be 5 steps here. I don't know why they only put 4 columns or 4 rows, because there has to be a 4th step that says the measurement of angle 1 is equal to the measurement of angle 4 based on substitution. In other words, if you combine 2 and 3, you get 4. And then finally, there's a 5th statement that says that AB is parallel to CD because the definition of parallel lines and
angles
and transversals.
Transversals.
Yeah, parallel lines and transversals. And I don't know what that's officially called. Once you get to that part, they'll tell you. But you can kind of see it's a lot tougher if you have to provide both columns. And they even make a mistake here. I'm quite certain that they need 5 rows and they only showed 4. Because I don't know how you can eliminate any of these rows. Anyway, that's what 2-column proofs are all about. And if you can get through this chapter, you'll be home free.
All right.
But it seems like you get it. So I think you'll be fine with proofs. All right, Cole. I will talk to you. Refresh me again. What's going to be our standard time on Monday?
3:30.
Okay, cool. That's what I thought. Okay. Yeah. Talk to you next week.
Talk to you next week.
Bye-bye.